Hello everyone, see you again. In today's course, I will introduce how to implement a computing virtualization to you. Actually, it includes three parts. The first part is CPU virtualization, the second is memory virtualization, and the last part is I/O virtualization. Let's start the first part, CPU virtualization.
Computational virtualization is divided into three areas, named CPU virtualization, memory virtualization, and I/O virtualization. Let's first look at the first virtualization, CPU virtualization. CPU virtualization is implemented by means of time sharing. It first appeared on IBM's mainframe until IBM opened up its own CPU virtualization technology. The virtualization of x86 architecture began to flourish. The first thing that comes out is VMware and SAN, and finally KVM. For security reasons, the CPU is divided into different protection domains, which are known as Ring 0, Ring 1, and Ring 2 and Ring 3. Only the operating system or driver instructions can run on the highest privileged ring 0. This command is called the call command or privileged instruction. Other applications typically run on ring 3, which has the lowest privilege. This type of instruction is called a user instruction. When there is a virtualization, there are two operating systems on one physical host. One is the host OS and another is guest OS. They all issue the privileged instruction. The hardware does not know the priority, so the sensitive instructions are issued by the guest OS, but they are deprived of privilege, and the instructions are all handed over to the hypervisor to execute the instruction. In the early days of CPU virtualization in the mainframe or mini-computer area, when the guest OS issued the sensitive instructions, the hypervisor could identify and capture them. Then use the interrupt mechanism to deprive the privilege and then simulate it by itself. After the operation is complete, the results are returned to the guest OS. However, in the x86 area, because of the instruction that of the CPU is different from that of the mainframes and the mini-computers, there are 19 sensitive instructions that are not core instruction and belong to user instruction. The only way to identify sensitive instructions in the core instructions does not work, so people develop some way to solve this problem. First two are full virtualization and parallel virtualization. In full virtualization, all core instructions and sensitive instructions will be captured and checked. If it is a sensitive instruction, it will be translated. If it is not put down, it will bring certain shortcomings affecting efficiency. It is very uncomfortable to keep stopping from checking your driver license on the highway. Therefore, the parallel virtualization is created. In the parallel virtualization, the guest OS knows that it is a virtual machine and then recognizes the sensitive instructions and sends them to the hypervisor for execution. It belongs to active report and the hypervisor only need to wait. So full virtualization and parallel virtualization are both over provisioning, and the ultimate solution is hardware-assisted virtualization. Whether the solution is a half virtual or full demand, it is because the CPU itself can only identify sensitive instructions and can only rely on software to identify. As virtualization applications become more and more widespread, the engines generated by the hardware can't sit still. Isn't it 19 instructions? I solve it for you. So they add new features to the CPU, which is our common VTX or AddamV function. It adds root and unroot privilege to the CPU, and CPU automatically recognizes the privilege and sensitive instructions. Then tell the hypervisor running in root mode to execute. The remaining instructions run in non-root mode, and then divide into different security levels in non-root mode. The running in ring 0 is still in ring 0. At ring 3, the basic we know are all hardware virtualization. So regarding CPU virtualization, we don't have to worry about whether it is all virtual or semi-virtual, because after hardware virtualization, it is basically all virtual. Next, let's take a look at memory virtualization. After the CPU is virtualized, the components and memory that are related to the CPU have undergone tremendous change. Why can CPU virtualization lead to memory virtualization? Because with the advent of CPU virtualization, virtual machines run on top of the VMM layers, replace physical machines, and become carriers for carrying servers and applications. And there are multiple virtual machines running on one physical machine at the same time. Then the problem comes. The physical host usually has only one or several memory modules. How to allocate memory resources in response to the requirements of multiple virtual machine memory? Obviously, the solution to the problem is virtualization technology. So, memory virtualization technology has emerged. But memory virtualization also encounters a problem, that is how to allocate the space of memory. There are two requirements when the physical host used in memory address space. First, we all know that the memory address starts from 0 in the physical memory, and the memory address space must be contiguous. So, after the introduction of virtualization, it is clear that there is a problem. That is, the space that requires a memory address starts from 0, but the physical memory has only one 0, which cannot satisfy the memory usage of all virtual machines. Second, the address is continuously allocated, and there are some solutions to solve the problem, even if it can allocate continuous physical memory for the virtual machine. But the memory usage is not high, and the flexibility is not good. The solution we use to solve this problem is to map the address. When doing the memory virtualization, we introduce a new address space, which is physical space of the client. Let the client feel that it's running in a real physical address space. In fact, the physical address is mapped in the virtual machine by the VMM. This perfectly solves the two problems we had before. Each virtual machine considers its own address code to be 0-based. That is what we saw on this graph. Each virtual machine considers its address are continuously, but the address it actually mapped to the physical machine are actually fragmented. The middle of this function is completely done by VMM, and this is memory virtualization. And the final area of computing virtualization is I/O virtualization. It is divided into three types. 1, 2, 3. 1 is emulation. 1 is parallel virtualization. And the last one is I/O throw. For emulation and parallel virtualization, when we talk about key VM, let's take a key VM as an example. In short, the performance of this emulation is not as good as the parallel virtualization performance. Then there is one that is I/O throw. I/O throw is not covered in the version of virtualization. I will briefly talk about it here. I/O throw is equivalent to hide a real physical device such as my mouse or my keyboard directly to a virtual machine. For example, I have 10 virtual machines running on this physical machine, and then only one set of mouse or keyboard. Then I only use my own mouse and keyboard to assign a virtual machine to use. This is called I/O through. The operation of I/O is not through the hypervisor. It is equivalent to the real physical device directly used for virtualization. This performance is the highest, but there is a premise that it needs hardware support. If the hardware does not have this function, and this can't be done. So far, we have finished computing virtualization and to focus on CPU virtualization, memory virtualization, and I/O virtualization. There are different knowledge of this part, and everyone should check the relevant document, some of the surrounding information, and try to master as soon as possible.
Okay, everyone. When we finish this course, I believe everyone have known how to implement computing virtualization. And in next course, I will introduce the relationship between cloud computing and virtualization. Besides this, I will introduce KVM and then to you. See you.